no need for read-write pin, right? So there is no need for this pin, because it's always a read operation. And there is no need for data in, because I don't write, I just read. So I need just data out. This is why for ROMs we have just the address bus. So if I have, for example, this 16 by 8 ROM, this example, this means the 2 power 4 2 power 4, this means I have 4 address lines, and I have 8 data output lines, yeah, for the data bus. And here I have the chip select. Do you see here, I put for CS, some number is the chip enable or the chip select is active low. Do you see this circle here? And even in the name I put TS bar. You can find many memories, they are active low, which means to enable the memory we put 0, not 1. 1 0 for enable, 1 for to disable. So you need to be careful. Wherever you see a circle, if you go to the data sheet of any device, I'm not talking about only memory, any device, when you see a circle like that next to the pin, this means this is active low. You know, do you remember the inverter? The inverter, we have a circle. So whenever you see the circle, even in all the NAND, we have a circle. The more, we have a circle, right? So the circle means it's active low. So you need to be careful, yeah? So it's the inverse logic, but of course the operation is the same. How the memory operates is exactly the same. I think this is the same example that I have provided. It's a continuation of the example. So assuming that I have this memory, 16 by 8, and this is the data, I put the data here in hexadecimal. Of course, this will be binary, so D0 to D7, this is the content. For example, if you go to read, or for example here, this location, 001, 0011, which is 3, right? So it's this location, 3. The content of this location is AF. So AF in binary is this one, right? This is F, this is A. So this is the content of this memory. So to read data, we need to apply the address on the address lines and activate the control inputs, yeah? So to read location, if I want to read this location, what is this? It's 7, right? This is 7. So this is 7. So what is the content is ED. This is the content. So I need to push this on the address bus, right? So A0 should be 1, A1 should be 1, A2 should be 1, and A3 should be 0. CS should be low, 0, as I told you, this memory is active low. And then if I go to the data output, this will appear on the data output. And again, this is D, and this is E, right? ED, this is the output that I will get. And again, this content will not change. It always stays forever until until you change your circuit or you throw your device or whatever. So once it's programmed, then that's it. Right. I don't know why this one. Random access. One important point of this, of course, I mentioned it anyway, but the content is non-volatile, so it doesn't. We do not lose the content when we power off the device. So you have the device, you disconnect it from the power, you connect again, the data is there, it doesn't go. which is not the case for the RAM access random access memories. Random access memories we can read and write from it. So which means we have all the pins that we covered in the previous slide, and then we have the content is volatile, so it disappears when we disconnect. Then that's it; it goes. So when you start the system, and this is what we said last time. Do you remember when the RAM? We have in the embed we have a flash memory. Flash memory is like the RAM. I mean, or it's like a hard drive. When you save the data, you save the code there, it stays there. Even if you power off the device, it stays there. And then once we power on the device, the code goes from the flash memory to the RAM, and then the microcontroller starts the execution, because it will not stay in the RAM when you disconnect your embed. So this type of memories is faster. You know, the read and write operations are faster with it. They are, close to the CPU as well. And of course, we can read and write from it. As we said, the two types of operations that we have can be performed on this memory. So this is an example of two memories. We have the first one, the 21478 memory, which is 4K by 1. What does this mean, 4K by 1? This means the memory location, each one is 1 bit, just 1 bit. So which means we have data out, 1 pin for data out, 1 pin for data in. So this memory has separate lines for inputs, data inputs, and data outputs. And of course, because it's 4K, 4K is equal to 4 power 2 by 2 power 10, which is equal to power 12. So which means we have 12, this is 12 bits for the address. We have, again, as you can see here, CS bar. It's active low, and we have read write. We have as well this chip, for example, which is from Motorola, MCM62063, 32K by 8. So the size of each memory location is 8-bit, and as you can see here, the data bus is bidirectional. So we have from 0 to 7. It's bidirectional, so we have just one bus, input, output. We have read and write. We have CE, and it has another pin here, as you can see, which is called output enable. So you can even disable the output. So you can use it, you can read. If this one is disabled, you can just read, you cannot write. Oh, sorry, you can just write, you cannot read. The output is disabled. So it has an extra control line. And then, of course, the data, because we say is 32K, which is equal to 2 power 5 by 2 power 10, which is equal to 2 power 15. So I have 15 from A0 to A14. I have 15 lines for the address bus. And the size of each memory location is 8 bits. Right. Last slide, just a simple example here. So what is the size of the address bus of a RAM with 4M memory locations? Can someone answer this question? Can someone answer this question? So if I have 4M memory locations, what is the address bus size, the size of the address bus?
Doctor?
Yes.
It will be 22.
Yes, why 22?
I did len 4 to 10 to power 6 over len 2.
No, what is 4M?
It is the word, memory word, or...
Yeah, if you write this as a power of 2, what do we get? Yes. So, Muhammad.
Yes, Dr. 2 power 2 times.
Times 2 power 20, right? Because
Yes.
you said m. 2 power 2 mega is 2 power 2 times 2 power 20, which is equal to 2 power 22. So the correct answer is 22. So it's correct what you said. So you just write for m as power of 2, and then that's it. What you get here is the address bus, the size of the address bus. So the answer is correct. You use different methods, the logarithm Neperian, which is okay as well, which is correct. But it's easier to write it as a power of 2, and then that's it. Yeah. Yeah. So for your case, you put for m is equal to power x, and then you get x. Yeah. As a logarithm Neperian, which is fun. Now, next question. How many individual memory locations, now we are asking about memory locations, how many memory words can be accessed if I have 10 address lines? Yes, Tamim. Yes, Tamim, go ahead. We cannot hear you. I don't know, you have a problem, Tamim, with your device. I don't know what are you using, but we cannot hear you. Yes, Muhammad?
It will be 2 to the power of 10,
Yes.
which will be 1024, which is 1K.
Which is 1K. Good. Right. So that's it for this lecture.